So I'll be giving a brief overview about internal waves and how they are relevant to various geophysical flows in ocean and atmosphere. So the cartoon on the right-hand side shows you a stable stratification being present. What I mean by stable is a lighter fluid sitting on a heavier fluid, and it's a continuous stratification. And in this case, it's a linear stratification. And each horizontal layer is a constant density surface. So if you perturb the fluid, this density interface undergoes a wave-like motion, and that's what exactly is an internal wave. So you have such type of stratification being present both in atmosphere and ocean. In atmosphere, the density is mostly the function of temperature, and the order of magnitude is, say, so on the y-axis you have the altitude in kilometers, and on the top x-axis you have the density. So in the top 100 kilometers, what we consider as atmosphere, you have an order of magnitude of 10 power 4 increase in the density values. Whereas in ocean, you have at the most 1% increase in the density value as you go from the free surface to the deep ocean. So the dynamics of internal waves is quite different when compared with each other. So these are the signatures of internal waves. On the top right is a peculiar example which is called as the morning glory waves in Gulf of Carpentaria. This happens only once in a year in a place in Australia. So what you see is the internal waves propagating from the ocean towards the land. And this is a very particular case of internal waves called as internal solitary waves. So the wavelengths and amplitudes here are of the order 300 meters. And what you see along the crest length is of the order 1,000 kilometers. So these are huge waves which propagate once in a year in this particular location in around the month of September. And the white color which you see, it's the clouds trapped in the internal waves. So there are people who are adventurous. They go and jump over these waves from aircrafts, and they with the gliders, and they do surfing over these waves. And the next example is internal waves. Internal waves is an ocean. This is a satellite picture. It's in the Solus Sea. So you have trains of internal waves which propagate towards the coast. And here also the order of magnitude of wavelength is around 300 meters. And the along crest length is of the order of 1,000 kilometers. And the next image is an ocean observation in the top 500 meters. So you take the 50 to 100 meters, the density layers, and when they use an instrument called as echo sounder. This measures the displacements of the density layers, and it's the order of 150 meters. So there are these huge waves present in both ocean and atmosphere, but they are also present in various other locations, but you can't just see them with the naked eye. And what you call as surface waves in ocean is a limiting case of internal waves, where you have just a two-layer stratification and the interface moving as surface waves. So this is about the natural frequency of this density stratified flows. So when you displace a fluid particle from a position, say from 2 to 1, where your ρ2 is greater than ρ1, so if you do the force balance, you'll see that the natural frequency of the oscillation of this particle is what is given by Brunt-Vaisalla frequency or the Banerjee frequency. So what you basically need for internal waves is just a stratified fluid, and you give it a disturbance, and this disturbance propagates as a wave called as internal wave. So the motivation, as I come from an aerospace background, people ask me why you study internal waves. So the main motivation for me is the clear air turbulence. So when you travel in an aircraft, there's always the pilot giving you instructions that you're going to face a clear air turbulence. So what exactly a clear air turbulence is? You have a disturbance, say a mean flow over a topography. So this density surfaces get disturbed, and they propagate as internal waves. And as they propagate, they transfer both energy and momentum, and they locally deposit this energy and momentum. And wherever they deposit this energy or momentum, they cause turbulence. And that's what exactly is a clear air turbulence. So as they propagate, there are various instabilities involved, which lead to the CAT or the clear air turbulence. So this is the DC-8 cargo jet accident. So this happened in the state of, above the state of Arizona, where this aircraft was traveling over this, in the atmosphere. So it faced a clear air turbulence, due to which the right wing just ruptured, and there was an engine with the engine, but the pilot could control the flight and they could land it safely. So Clark et al. Did a numerical simulation, both using the observed data and as well as considering a 3D domain and doing a direct numerical simulation. And what they found, the reason was it's due to the CAT, that's a clear turbulence, due to the interaction of jet streams and mountain force internal gravity waves. The next phenomenon is more related to ocean. So Nansen, during his North Pole expedition, there's a good book written by him about his exploration, where he says that on some days when he's traveling, he moves with a speed of around 12 knots, but on some other days, it becomes very slow, and he didn't know the reason of why it happened. So people later studied it. The Ekman was the first guy to find it. So they say, so when the ship is moving, it transfers some energy to this interface, and this interface gives an additional drag to the ship. So that's the reason why which the ship slows down. And recently, Marcia et al. Did an experiment where you see a 2D stratified flow. So the red color is it's just the water, and below it is the stratified fluid. So at the interface, so there is an arrangement by which they move the boat just horizontally, and as they move it, you find the interface propagating, and the energy transfer due to the moving of the ship to the waves, and that results to its motion becoming slow. So the next example is on the ocean turbulence. So this is a picture taken from top paper. So when you talk about ocean, it's the tidal forcing. So it's like the ocean moving back and forth about the ocean bottom topography, due to which as it moves back and forth, it hits the deep ocean topography, and there's an internal wave generation. And there are various other forcings, like you also have surface winds, which give a surface forcing, and you have internal wave propagating downward. And you also have horizontal stratifications being present due to the river inflow. And so in this case, you have a horizontal density stratifications and the internal waves moving vertically downward. So in case of ocean turbulence, it's said like the way JKB was explaining. In the large scales, you have the energy coming from the tidal forcing, and in the small scales, it's the heat dissipation. And how the energy transfer takes place from large scales to small scales was studied by Monk and Wunsch. It's a classical paper where they do ocean energetics, and they get to the conclusion that it's the energy transfer due to the internal waves which propagate. And as they propagate, they break down, and there are daughter waves created, and there are various other instabilities involved. And and in the process, they reach finally to the viscous dissipation. So now I get to the theoretical part. So these equations are quite familiar. These were the similar type of equations which J. Sukatme showed you for the quasi-geostrophic flows. So you have a 2D inviscid, incompressible, and F-plane and Bushnell's approximation. But in the classes, he showed you the XY plane. What I'm going to study is in the XZ plane, where you have the waves propagating in the X direction and the stratification being present in the Z direction. So you do a cross product for equation 1 and 3. You can eliminate the pressures. Then you can replace the V here from the W here from this equation. And you can simplify it to a simple single equation, which is called as a linear internal wave equation. I've also neglected the advection terms. So this is a simple linear equation with just n, which is the buoyancy frequency. If it's a uniform stratification, your n is constant, so you can directly analytically solve it. But if it's not in uniform stratification, your n will have a particular ocean-like density profile being present. Then you solve it by numerically. So you can look, the solution is of the form this. So you have cos knx minus omega t and phi n of z giving you the mode shape in the vertical direction. So if it's a non-uniform stratification, you can like substitute this equation, solution in the equation to get a governing equation for phi n, which can be numerically solved to get kn and phi n. So for uniform stratification, you have this case where your phi n will be simply sin n pi z by h, and the horizontal wavelength, horizontal wave number would be n pi by h cot theta. So these are, this is the modal representation of the internal waves. So these are pictures of stream function for mode 1, mode 2, and mode 3. The horizontal domain is taken to about wavelength corresponding to mode 1. Next, about the properties of internal waves. So when you substitute, say if you're looking at just the uniform case, when you substitute for k, just substituting this kn and phi n's in the equation, you can get a dispersion relationship, which goes as this: cot theta is n square minus omega square, and this is m by k, where m is your vertical wave number and k is the horizontal wave number. So if you just look at this dispersion relationship, your n is fixed by the stratification which you consider, f naught is fixed by the f plane which you are working on, and it's just the omega which you can vary, the forcing frequency. And depending on the forcing frequency, it determines the direction in which the wave propagates. So this is one of the peculiar properties of internal waves, where you just define the forcing frequency, and that gives you the direction of wave propagation. Go ahead and calculate the group velocity, which is defined in this way, and you see that the direction of energy propagation, which is the group velocity direction, and the phase propagation, which is the wave vector direction, are orthogonal to each other. So this is an experiment to show that whatever physical properties I've told just now. So there is a density stratified fluid here. This was done by Mowbray and Rayeti in 1967. So what you have is a cylinder which is getting oscillated vertically, and you see internal wave beams propagating in the 4 directions. That's why it's called an St. Andrew cross. So as you vary the frequency, you'll see that the phase propagation, which is shown by yellow arrow, it moves towards upward, and the energy propagation is always orthogonal to the phase propagation. And this is done by using shadow graph technique.